good afternoon. Today we will start the third lab section, which is the determination of hydraulic conductivity. It is one of the most important engineering property that we can measure about soil because if you remember from your soil mechanics class, you need the hydraulic conductivity to help you evaluate seepage and then maybe evaluate whether the soil likely to have a flow behind retaining wall, etc. So you will need to determine hydraulic conductivity. So usually for hydraulic conductivity, the symbol is K. The unit for this parameter is length per time, okay, length per time. So for example, it can be centimeter per second or meter per second. So today we are going to use laboratory methods to evaluate the hydraulic conductivity. In fact, there are many methods that you can use to determine this parameter. In the field, you can use some field methods. In the lab, you can use some direct methods called, for example, called the constant head test or falling head test to find out this K value. In addition to these two tests, you can also perform consolidation test and then also the triaxial test to indirectly obtain this K value. But for today's lab, we are going to focus on the constant head test and falling head test. So let's look at the constant head test. The principle behind this test is as follows. So first of all, this is the schematic diagram for the constant head test. So you will have a sample and then there will be water flowing through this sample. This sample has a cross-sectional area of A, which is this area here. Okay, and then there is inflow and outflow of water. Okay, so there will be some valve indicated as the red here, which you can turn on and off. Okay, so that the water can flow in and flow out of this device. So what we are going to do today is basically measure the K for this sample, and the way to obtain that K is to obtain the head at various locations of the samples. So if you go to the lab, if you look at the setup of this lab, there will be a manometer or piezometer that is installed near the top and then also near the bottom of the sample. The manometer or the piezometer can help you, can basically let you know the head of the sample. So as you learn from your soil mechanics class, okay, the water will flow from a location with higher head or higher energy to a location with lower energy. Okay, so if you look at this graph here, the head corresponding to this location should be higher than the head corresponding to the bottom of the sample. So if you look at the difference in the water level inside the manometer, you will see that the water level will be different, and then the distance between the water level would be the h, which is in fact equal to the head difference between these 2 points. If you use Darcy's law, okay, if you remember Darcy's law, basically it would be the velocity equal to hydraulic conductivity K times I, and then if you consider the flow rate, which is denoted as Q, it would be equal to K times I times A. Okay, K is the hydraulic conductivity, I is the hydraulic gradient, and A is the cross-sectional area which the water flows through. Okay? And for the I, it would be equal to the head difference divided by the length. Okay? So in this case here, this h would be this distance, and then the length would be the length of the sample, which is this distance here. Okay, so if you follow the derivation from your soil mechanics class for constant head test, the hydraulic conductivity can be calculated using this equation. Okay, so you will need to look for the derivation from your soil mechanics reference textbooks. So in this test here, what we are going to do is to is to measure Q. From Q, because L, H, and A can be obtained from the test, we can calculate K. So what we have to do is, for a certain period of time, we will obtain a certain amount of water that flow out of this device. So what we're going to do to obtain Q is to measure the mass of this beaker with the water. So suppose that you measured the mass that is coming out of this setup within 20 seconds, then you will determine or measure the mass. Okay, so for an example, okay, here, suppose that you obtain 800 cc of water in 20 seconds, then you will be able to obtain the flow rate, which is equal to 40 centimeter cube per second. Okay, so that's how we determine the Q. L is the length of the specimen, which is fixed, and then you can measure it from the device. H is the head difference. So again, you can look at it from the setup. And then A is the cross-sectional area, which is determined by the diameter of the sample. So in this test here, we are going to select several H value. Okay, you are going to basically obtain an H and then observe for a particular H value what kind of K you will observe. Okay, so this is the principle behind the constant head test.